you have completed this section. All right, everybody, welcome back. We are now headed into lesson 4, Remix Fund Me. And of course, all the code can be found on the GitHub repository associated with this course. We're going to be working with 2 contracts here. One of them is fundme.sol, and then one of them is priceconverter.sol. Fundme.sol is going to be a contract that allows people to actually fund a collective good. So people can send Ethereum or Polygon or Avalanche or Phantom or whatever blockchain native token into this contract, and some owner of the contract can then withdraw those funds and do whatever they want. After deploying this to a testnet, we can see the list of functions this contract has. This will have 2 red buttons, which are used to notate 2 payable functions in our fund function, and in our withdraw function. Withdraw allows users to withdraw the funding, and fund allows users to send money to the contract. What we can do is we can send some value along with our transaction when we call this fund function. And then what we can do is we can actually fund this contract with a certain amount of ETH or WEI by pasting some value into the WEI value section and then hitting fund. We will now have sent money into our deployed contract, and we can see a list of the funders and a mapping of those addresses and how much they've actually sent into the contract. We can then withdraw the funds out of the contract, with a special exception with only the person who deployed this contract can actually withdraw the funds back out. Once the funds are withdrawn, the amount of all the funders is reset back to 0. Are you excited? Well, you should be. And if you finish this section, you'll have completed most of the basics of Solidity, and you'll be ready to start making even more powerful smart contracts. We'll be using Chainlink price feeds to actually set the value of how much these people should be able to fund in USD as opposed to just in terms of Ether. We're going to go over a lot of advanced sections here, and I'll let you know what parts might be a little bit harder to digest so you don't have to spend your entire time trying to figure out exactly what's going on. Be sure to use the GitHub repo to your advantage here and the discussions tab to stay connected with other people taking this lesson. All right, let's jump in. So at this point in Remix, you'll have a couple of contracts here. Simple storage, storage factory, extra storage. Maybe you refreshed Remix and these have gone away. In any case, make sure that you just don't have any of those tabs open. We're going to create a new contract called FundMe. So let's go ahead and start creating our FundMe contract. Again, we want it to be able to get funds from users, withdraw funds, and set a minimum funding value in USD. This is what we're going to get our contract to do. So first, let's set it up. SPDX, license identifier, MIT. We'll do pragma, solidity. We'll do caret, 0.8.8, and we'll do contract, fund me. Awesome. And we'll compile, see if things look good, and they do. Great. Let's keep going. So before we actually embark on creating all of our functions here, let's just add the different functions that we're going to implement. So we want a function fund for people to actually send money to. We want a function withdraw for the owner of this contract to actually withdraw the funds that different funders actually give us. And that's pretty much it. These are the 2 main functions that we want this contract to do. We will be implementing more functions to help facilitate these 2 functions. But let's get started by looking at fund. Let's comment out withdraw for now, and let's just start with fund. So we want anybody to be able to call this fund function. So we'll make this public. So as we mentioned, we want to be able to set a minimum fund amount in USD. So there's a lot of things to think about here. First thing we probably want to think about is how do we send ETH to this contract? Whenever we create a transaction on any of these EVM blockchains, there's this value field that we can set. Value represents how much Ethereum we're going to be sending with our transactions. For example, when we transferred Ethereum between our different accounts, we were actually populating this value parameter with different amounts of Ethereum. In fact, every single transaction that we send will have these fields. It'll have a nonce, or the transaction count for the account, the gas price, the gas limit that we've seen on Etherscan, a to, aka the address that the transaction is sent to, a value, which is going to be this amount that we're talking about. We'll also have data, which is going to be what we send if we make a function call or deploy a contract. And then it'll have this VRS components. We're not really going to go over these VR and S because this is that cryptographic magic that's happening when a transaction is signed, but just know that that's in there. For sending value, we can populate some of these fields. The gas limit, for example, is populated to 21,000. Data is going to be empty, and then that 2 is going to be the address of the transaction we want to send to. For a function call, we can also still populate the way that we want to send. So we can call a function and send a value at the same time. In Remix, it has a little drop down here for way, gway, finny, and ether. We're going to ignore finny for now, but of course we have our way, gway, and ether again, where 1 ether is worth this much gway and this much way. The first thing we need to do in order to make a function payable with Ethereum or any other native blockchain currency is we need to mark the function as payable. It's this payable keyword that makes our fund function red as opposed to having it normal orange. Just like how our wallet can hold funds, contract addresses can hold funds as well. Since every time you deploy a contract, they get a contract address, it's nearly the exact same as a wallet address. So both wallets and contracts can hold native blockchain token like Ethereum. And you'll see that when we deploy this later on in the lesson, that it actually will gain a balance of Ethereum. Now that we have it payable, we can access this value attribute by using one of the global keywords in Solidity with message.value. To get how much value somebody is sending, you use message.value in your function. Now, let's say we wanted to set our message.value to a certain value of Ethereum. Let's say we wanted people to send at least 1 whole ether with all their transactions. Or put another way, if they sent Ethereum, they would need to send at least 1 Ethereum. How would we implement that? Well, we could use something called require. We would say we would want to require the message.value is greater than 1E18. There's a couple things to unpack here. 1E18 is equal to 1 times 10 raised to the 18th, which is also equal to 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8. This is the value in way of 1 Ethereum. This much way is 1 ETH. So if we wanted the message.value to be at least 1 ETH or 1 Polygon or 1 Avalanche, etc., we would set it like this. Require message.value is greater than 1. This require keyword is a checker. It says, hey, is message.value greater than 1? If not, it's going to revert. It's going to do what's called revert with an error message. And we can say, didn't send enough. We can try deploying this on a JavaScript VM. We'll deploy FundMe. We'll hit deploy. Look at FundMe. We see this fund button is now red. If we call FundMe right now, and we look at the console, you can see we actually get an error here. Call it again, we get an error. We get an error here. We know that the error is going to be this, didn't send enough. So what we need to do is we need to send at least 1 ETH with this fund transaction in order for this require statement to be fulfilled. So back up in the value section, we can change this value to 1. So that's going to be 1 ether or this much way or this much gway. Now we can hit fund. Oh, actually it needs to be greater than 1. So let's send 2, for example. Now we'll scroll down and now we'll hit fund. And we see that that actually passes. The require statement says, if our first section is false, then go ahead, revert with this error. What is reverting? Revert can be a little bit confusing. So I wouldn't let this section hold you back if it's a little bit confusing. Revert is when it undoes any actions that happened before and sends the remaining gas back. So what does that actually look like? Well, let's say, for example, we get a uint 256 public number. And in our fund function, we said number equals 5. If we were to go ahead and deploy this, let's delete our old contract, deploy this new contract, our number right now is 0, but if we were to call our fund function, number gets set to 5. However, if we call fund and this require isn't met, this transaction would revert and undo setting number to 5. So let's go ahead and look at our logs here. We'll keep value to 0 so that our fund function reverts. We'll call fund. We'll see that this transaction failed because this require ended up reverting and number is still 0. So then the question becomes, did we actually spend gas? Yes, we spent gas to change number to 5, and then any remaining gas we would get returned by this require. For example, if we had a ton of computation here, we would have need to send a ton of gas with our fun function. But all of the extra gas that we send after this require gets returned to the original user after it gets reverted right here. If reverts are a little bit confusing for you here, don't worry too much about it. We'll go over it in future modules. All you need to know right now is that when you do a require statement, if this first section isn't met, the transaction will be canceled and any prior work will be undone and it'll send an error message. So cool. Let's delete this number for now and we'll delete it from the global scope. There's actually another way to do these reverts, which we'll go over later in this contract. So what we've done so far is great. However, we're checking message.value in terms of Ethereum. We're looking for one whole Ethereum instead of $50. We want to check that message.value is greater than some number like $50. Let's go ahead and first set the minimum USD value we want people to send along with the fund function. We can do that at the top of our contract. We can say UN256 public minimum USD equals 50. Now we have some place to check for minimum USD. We're going to update this minimum USD to make it more gas efficient in a little bit. Now that we've set our minimum USD, we want to be able to require the message.value is greater than, or let's say greater than or equal to the minimum USD. But minimum USD is in terms of USD and value is in terms of Ethereum. So how do we convert Ethereum to USD? This is where oracles and Chainlink are going to come into play. The USD value of Ethereum is something that we've assigned outside of the blockchain to each Ethereum or any other layer 1 currency or any other native smart contract platform currency. So in order to get this value that is outside the blockchain, we have to use a decentralized oracle network to get the price of 1 Ether in terms of USD. So before we can continue on here, let's learn a little bit more about the architecture of these decentralized oracle networks and the different solutions that they have so that we can create this FundMe contract in the most advanced way possible. As we've talked about, blockchains are deterministic systems, which means that they themselves can't actually interact with real-world data and events. They don't know what the value of an Ethereum is. They don't know what random numbers are. They don't know if it's sunny outside. They don't know the temperature. They don't know who's president. They don't know any of this information. These blockchains also can't do any external computation. Maybe you have some amazing artificial intelligence model that you want to integrate with a smart contract. Smart contracts by themselves can't do anything with that. As we've mentioned, this is because blockchains are deterministic by design. This is so that all the nodes can reach consensus. If you start adding variable data or random data or values that return from an API call, different nodes could get different results and they would never be able to reach a consensus. This is known as the smart contract connectivity problem or the oracle problem. And this is bad news because we want our smart contracts to be able to replace traditional agreements. And traditional agreements need data and they need to interact with the real world. So this is where Chainlink and blockchain oracles come into place. A blockchain oracle is going to be any device that interacts with the off-chain world to provide external data or computation to smart contracts. However, the whole story doesn't even end there. If we use a centralized oracle, we are reintroducing a point of failure. We've done all this work to make our logic layer decentralized, but if we get our data through a centralized node or through a centralized API, or we decide we want to make the API call ourselves, we are reintroducing these trust assumptions that we've worked so hard to get rid of. We're essentially ruining the entire purpose of building a smart contract. So we don't want to get our data or do external computation through centralized nodes. Those are bad news. Chainlink is the solution here. Chainlink is a decentralized oracle network for bringing data and external computation into our smart contracts. As we mentioned before, this gives rise to these hybrid smart contracts, which combine on-chain and off-chain to make incredibly feature-rich, powerful applications. Chainlink is a modular, decentralized oracle network that can be customized to deliver any data or do any external computation that you like. So, for example, a lot of people say, oh, I can just make an HTTPS call to some API and we'll be good to go. The blockchain nodes can't make these HTTPS calls because they wouldn't be able to reach consensus. If they called the node at different times or they did something else, all the consensus would be broken. So instead, we need a decentralized network of Chainlink oracles to do this. And then in the transaction, this network of nodes will return the data to our smart contracts for us. Now, Chainlink networks can be completely customized to bring any data or any external computation that you want. However, doing the customization can be a little bit extra work. There are a ton of Chainlink features that come out of the box completely decentralized, ready to plug and play into your smart contract applications. What are those features? The first one is going to be Chainlink data feeds, and that's the one we're actually going to be using for our application here. Chainlink data feeds, currently at the time of recording, are powering over $50 billion in the DeFi world. The way they work is a network of Chainlink nodes gets data from different exchanges and data providers and brings that data through a network of decentralized Chainlink nodes. The Chainlink nodes use a median to figure out what the actual price of the asset is and then deliver that in a single transaction to what's called a reference contract, a price feed contract, or a data contract on chain that other smart contracts can use. And then those smart contracts use that pricing information to power their DeFi application. We can see an example at data.chain.link. And you can change networks, you can change price feeds, you can change a whole bunch of different information to see some of the most popular price feeds. Let's look at ETHUSD, for example. On ETHUSD, we can see this whole network of independent Chainlink node operators that are each getting different answers for the price of ETHUSD. They're getting aggregated by the network and then delivered on chain. We can see how often they're updated. These ones are updated for a 0.5 deviation threshold or a few hour heartbeat, whichever one hits first. We can see when the last update was, we can see the number of Oracle responses, etc. We can see the contract address directly on chain. We can even look at the contract on Etherscan. We can see some of the history. We can see all the responses of the different oracles. And then at the bottom, we can see the different users and sponsors keeping this network up. Similar to transaction gas, whenever a node operator delivers data to a smart contract, the Chainlink node operators are paid a little bit of Oracle gas in the Chainlink token. Right now, these users of the protocol are sponsoring keeping these feeds up and are paying the Oracle gas associated with delivering this data on chain. Here's an illustration of what the current model of these data feeds look like. A network of these Chainlink nodes each reaches out and gets the information about an asset and then signs the data with their own private key. In a single transaction then, one node will deliver all the data with all the different signatures to a reference contract. If that node doesn't deliver the data, another node will send it instead. Reputation is incredibly important when you're a Chainlink node operator. If you miss data updates, if you forget to send transactions, you'll probably be quickly kicked off these networks and have no chance of making any more money in the future. These data feeds are used by some of the largest protocols in the space, such as Synthetics, SushiSwap, Compound, and Aave, with several $1 billion each. We can take a look at an example over at docs.chain.link. Work with EVM contracts. We're going to hit EVM chains, scroll down to data feeds. We'll scroll down to the Solidity section, and we can see an example of an entire contract that uses and reads from one of these Chainlink price feeds. We can even open this up in Remix and work with it in Remix. It looks like this example is reading from a price feed on Kovan. The reason we're actually going to use a testnet to see this work is that there's a set of Chainlink nodes monitoring the test network to show you exactly how this works out. Once we get deeper into the course, we'll show you how to actually run tests and work with Chainlink nodes without actually being on a testnet, which will make your development much faster. But I highly recommend walking through this section along with me so that you can see firsthand how this actually works. So let's go ahead to faucets.chain.link/Kovan. We're going to switch to the Kovan network and we're going to get some Kovan ETH. But remember, look at the network flag and use whatever network is in the documentation. So to get some Kovan, we're going to come to the faucet. We're going to turn off test link. We'll just stay with ETH. I'm not a robot. And then send request. Once our Kovan Ethereum has reached our wallet, we can go ahead and close. And we can take a look in our wallet and see that we do indeed have 0.1 ETH on Kovan. Now let's go back to our remix. We'll compile this contract. We'll go and deploy this on injected Web3. And again, the reason we're going to use injected Web3 instead of JavaScript VM is that there's no network of Chainlink nodes watching our little fake JavaScript VM. There are a network of Chainlink nodes watching the testnet. So we'll scroll down, we'll switch contract to the price consumer v3, and we'll hit deploy. MetaMask will pop up, and after a brief delay, we can see our price feed consumer down here, and we can hit get the latest price, which shows us the latest price of Ethereum in terms of USD. You may be wondering why the number looks so weird. That seems like a really large number for the price of Ethereum in terms of USD. And this is because decimals don't actually work so well in Solidity. And we'll get to that in a little bit. There's a decimals flag associated with this price feed address that tells us how many decimals to include with this price. It's also in the documentation. However, I know that this one has 8 decimals. So this is saying the value of Ethereum right now is $3,262. It may, of course, be different when you go ahead and try this. Now, there's a number of things that happen in this contract that I'll explain in our FundMe example, but if you want to take a look now and see if you can figure out what's going on, I recommend you do so. Price feeds are one of the most powerful out-of-the-box decentralized features you can use in your smart contract to level them up, especially for decentralized finance. If you're looking for different addresses of different price feeds, you can check the contract addresses section of the documentation, choose the network that you want, and then scroll down and then look some of the different addresses of the different price feeds. For example, this address will give you the price of 1 ETH token in terms of Ethereum. This address will give you the price of the Apple stock in terms of USD, and so on and so forth. The next decentralized application right out of the box is going to be Chainlink VRF, or Chainlink Verifiable Randomness Function. Once we do our lottery example a little bit later, we'll talk about how randomness can be manipulated in blockchain. Blockchains are deterministic systems, which by definition means that they can't have randomness. If you can determine what a random number is, it's not really random anymore, is it? So we need a way to get a provably random number by looking outside of the blockchain. And oracles are perfectly positioned to do exactly that. Chainlink Verifiable Randomness Function is a way to get provably a random number into our smart contract to guarantee fairness and guarantee randomness of applications. Many protocols like Pool Together, Axie Infinity, Ether Cards, Avagochis, and more use Chainlink VRF for lotteries, for randomizing NFTs, for gaming, and for more. We're going to do an example of Chainlink VRF in a later section once we get to the lottery section. If you want to see if you can play with the randomness yourself right now, I recommend you going to docs.chain.link, EVM chains, and scroll down to get a random number. And this will teach you how to get a provably random number into your applications. The next decentralized out-of-the-box feature of Chainlink is Chainlink Keepers, which is decentralized event-driven execution. As you've seen, in order to kick off some type of transaction, somebody needs to spend the gas and somebody needs to sit down and hit the go button or hit the transact button or hit the send button. This is obviously a centralized vector if you have a decentralized application that needs to run at specific times or after specific events are triggered. Chainlink Keepers are the solution to this. Chainlink Keepers are Chainlink nodes that listen to a registration contract for different events that you specify to fire. Maybe you say every 10 minutes you want to do something, or once a week do something, or if the price of some asset hits some number, or maybe a liquidity pool is at a certain level. Whatever event that you want to code, you absolutely can. The Chainlink nodes constantly listen for these triggers to happen and check the different contracts for these triggers. Once a trigger returns true, the Chainlink nodes will then perform whatever action that you tell the Chainlink nodes to do. We're also not going to go over the Chainlink Keepers examples right now because we're going to get to them in a later module. However, if you want to try them out, go to docs.chain.link/Ethereum, go to making compatible contracts, and feel free to read the documentation and try it out yourself. The last out-of-the-box feature of Chainlink is the most customizable, but also the hardest to get correct. End-to-end reliability is the ultimate promise of our smart contracts, and we want and need them to be able to do anything. We want to be able to take any input and get any output. Making HTTP GET, HTTP POST requests is an easy way to customize our Chainlink nodes to be able to do anything. Remember how we talked about making API calls? That blockchain nodes themselves can't do that? Well, Chainlink nodes can do that. Chainlink nodes can make direct requests to any API that you specify. In order to do this, you both have to choose the Chainlink node and the URL/data to send the request to. This is a little bit trickier than Chainlink VRF, Keepers, or price feeds because you then have to be responsible for creating the Chainlink network that gets data from many different Chainlink nodes and many different data providers. But let's look at an example in Remix anyways. For this section, feel free to just watch since we are working with a testnet here. And testnets, as we've seen, can take a little bit of time. As long as you're familiar with what this process looks like, that's good enough. You don't actually have to try it if you don't want to. So we'll open up in Remix. We'll read through. It looks like this example is on the Coven network. So we'll go ahead and compile API consumer. We're going to go ahead and deploy on the injected Web3. We're going to make sure that we're back on the Coven test network. We're going to scroll down and we're going to change the contract to the API consumer. And we're going to go ahead and hit deploy. We're going to deploy this contract to the Coven testnet. And now we can call this function called request volume data to actually make an API call. Now, like I mentioned before, whenever we request data from a Chainlink node, we have to pay a little bit of Oracle gas or link token. In order to pay some link token, we're going to need to have link token in our API consumer contract. This is what's known as the basic request and receive model. To get link token, we go back to our faucet, and this time we'll select 10 test link for our contract. Let's go ahead and verify that we're human, and we'll hit send request. This time, instead of sending us Ethereum, they're sending us 10 test link, which is what's known as an ERC20 token, or more accurately, an ERC677. We'll get to understanding that a little bit later. We can see the asset in our MetaMask by importing the token. In order to get the token, we're going to come back to the documentation, and we're going to look up link token contracts, like that. We're going to go to the network that we just got the tokens on, which for us was Coven. We're going to copy this address. We're going to go to MetaMask, hit import tokens, paste that address, and hit add custom token, and then import tokens. And now we can see in our account one, we both have Ethereum and 10 link. Now that we have our link or our Oracle gas, we're going to send it to our API consumer. We're going to copy the address of the API consumer, open up our MetaMask. We're going to hit send, paste the address of our contract, switch the asset to link. For now, we'll just send 0.2 link. We'll hit next, and we'll hit confirm, and we'll wait for this transaction to go through. I chose 0.2 link because in this contract, there's a fee character, which tells us how much making an API call for this is going to cost. This one is actually 0.1 link. I send 0.2 just in case we want to make that API call twice. Everything that's going on in this function we'll explain in a little bit later section, but for now, I just want to show you what it looks like to use. Once we send the link to our contract, we can first check to see what the volume is. The volume is 0. We want to get the volume of the last 24 hours of the Ethereum asset. We're going to be calling this API, which has a ton of raw data, including one in specific called volume over the last 24 hours, which is going to be this number right here. Say we wanted to get this into our contract from this API. We're going to make an HTTP GET call to this API. And what's going to happen is we're going to make the request in one transaction, and in a second transaction, the Chainlink node is going to return the value and store it in this volume variable in the global scope. So let's go ahead and hit request volume data. MetaMask is going to pop up. We're going to go ahead and hit confirm. And you'll notice right away, volume doesn't update. This is again because we actually need to wait 2 transactions. We're sending a transaction for the request, and then in a second transaction, the Chainlink node is actually going to respond. And after a slight delay, the Chainlink node has indeed responded with the result of making that API call back to our contract. We'll go over this process a little bit more in depth in later sections. The reason that I wanted to show you specifically the API calls is because we're going to show you a real life example of how to use Chainlink VRF and Chainlink Keepers in a later lesson. Now, I know we've already gone over a ton, so let's do a quick review. In order to send Ethereum or whatever native blockchain token with a function, you need to mark it as payable. If you need something in your contract to happen and you want the whole transaction to fail if that doesn't happen, you can use a require statement. To get the Ethereum or native blockchain token value of a transaction, you can use the global keyword message.value. Chainlink is a technology for getting external data and doing external computation in a decentralized context for our smart contracts. Chainlink data feeds or price feeds are ways to read pricing information or other pieces of data from the real world that's already aggregated and decentralized for us. Chainlink VRF is a way to get provably random numbers from the real world into our smart contracts. Chainlink Keepers are a way to do decentralized event-driven computation. We can set some trigger, say, if this trigger hits, do something. And we get to define what the trigger is and what the do something is. Chainlink Any APIs is the ultimate customization of Chainlink nodes and allows us to connect to anything on the planet. To make this one production ready, we have to do the most work because it doesn't come already with a decentralized Oracle network like Chainlink Keepers and price feeds. We'll learn more about these Chainlink services as we continue in this course. Now, in order for us to figure out if our message.value is actually greater than the minimum USD that we set, we actually have to convert our message.value from its layer 1/Ethereum to the USD equivalent. So how are we actually going to do that? Well, first, we're going to need to get the price of Ethereum or Phantom or Avalanche or whatever layer 1 blockchain that we're working with. So let's create a function to get that price, to get that conversion rate. So we'll do function get price, and this is going to be the function that we use to get the price of Ethereum in terms of USD, so we can convert our message.value to USD. And then we're also going to do a function called get conversion rate. And these are both going to be public functions so that we can go ahead and call them and test them and do whatever we want with them. So in order to get the price, we're going to have to use one of these Chainlink data feeds to get the pricing information. And we can look right here at this contract to see what using one of these Chainlink price feeds looks like. What we're actually doing when we're interacting with this Chainlink price feed is we're actually reading from one of these contracts. There's a contract out there called the aggregator contract that has a function called latest round data, which returns a whole bunch of data, but namely this int price. And this int price is what we are interested in. Let's look at our get price function and figure out, how do we actually call this? Since this is an instance of us interacting with a contract outside of our project, we're going to need two things. What are those two things? We're going to need the ABI of the contract and also the address of the contract. So the address of the contract is going to be easy. We can get the address of the contract from the contract addresses section of the Chainlink data feeds. Let's scroll on down to RinkB, and we can find the ETH USD address on RinkB, and we'll create this contract so that it works on RinkB. So we're going to grab this address, we're going to copy it, and we're going to move back to our code here, and we're going to paste the address here. So great, we have the address now. We have the address of the other contract that we want to interact with. Now, how do we get the ABI? Well, what we did before with simple storage was we imported the entire contract into our code here. That's something that we could do, but that's actually a lot of code. So what's something that we could do instead? Remember, if we're looking at Remix and we look at one of the contracts that we compiled before, the ABI is really just kind of this list of the different functions and interactions you can have with a contract. The ABI itself doesn't actually need to include any of the logic. It just needs to include, hey, here are the different functions that you can call. For example, in this contract, we can call fund, we have get conversion rate, we have get price. They're not implemented yet, but they will be eventually. Now, there technically is another way to interact with contracts without the ABI, but for now, we're just going to ignore that. So how can we get the ABI? There's a concept in Solidity called an interface, and let's look at an example of an interface. If we go to github.com/smartcontractkit/chainlink, we can see a number of different contracts in the Chainlink repository. We can go to contracts, SRC, v0.8, interfaces, and we'll go to aggregator v3 interface.sol. And if we look at the Solidity in here, we can see a whole bunch of function declarations, but none of the logic is actually implemented in this. This is what's known as an interface. If we compile this, we'll actually get the ABI of a contract because it defines all the different ways we can interact with a contract. It doesn't actually say what these functions do, which is fine though, because we don't need to know what the functions actually do. Those are going to be stored in the contract. So what we can do is we can grab this interface from the code and paste it into our remix. Now, hold on, if you're following along, you don't have to copy paste this with me because I'm going to show you an easier way in just a second. So for now, feel free to go ahead and just watch. But once we have this interface aggregator v3 interface, we can now use this to make API calls. So now we could say aggregator v3 interface at this address, and the combination of these two give us that aggregator v3 contract with whatever code is here. If at this contract address, this aggregator v3 interface is valid, we can do something like .version. Let's look at this interface. Is there a version function? There sure is. So that means we could call the version function on this contract. So let's actually go ahead and copy this into a different section. I'm going to create a new function called getVersion just to illustrate this. going to be a public, it's going to be a view, and it's going to return the uint256. And we're going to split it up into two steps here, but we're going to say aggregator v3 interface price feed. So we're creating a variable of type aggregator v3 interface equals aggregator v3 interface at this address. And then we're going to return price feed dot version. Now I'm going to go ahead and deploy this contract to Rinkeby just to show you what this get version is going to return. But you don't have to follow along here if you don't want, because again, we're working with the testnet. You can just watch if you like. For this section, we are going to test a little bit more sparse since we're going to be mainly using the testnet, since we're going to be working with an actual Chainlink Oracle network. Once we move over to Hardhat and with JavaScript, all this testing locally will be a lot easier and a lot faster. You're more than welcome to go ahead and fiddle and try and test a lot of this stuff as we go along, but just note that it might take a little bit longer to do some of the testing on a testnet. Let's delete that last funding contract. We're going to deploy this one. We're going to scroll up. We're going to switch to injected Web3. We're going to switch from Kovan to Rinkeby. And the reason we want to make sure we're on Rinkeby is because this address is specific to Rinkeby. The contract that we're looking to interact with might not be at this address on every single chain. We want to make sure we're on the Rinkeby chain for this, because if some other contract is there on a different chain, this version function obviously won't exist, and this function could error. So let's go ahead. We'll go to FundMe. We're going to deploy this to the Rinkeby chain. Again, you don't have to follow along with me here. You can just watch. And once that contract has been deployed, we now have a view function called getVersion, and we can see it's returning the variable 4, showing us that this is the 4th version of a price feed. So this is a really easy way for us to interact with contracts that exist outside of our project. We use one of these interfaces, which can get compiled down to the ABI, and then we combine that ABI with the address to call a function. As we work with these interfaces more and more, they'll start to make more and more sense. So if it's a little confusing to you right now, don't get discouraged. The more you work with it, the easier it'll become. Now that we know how to call these functions in here, we can start working with this interface. However, as you know, if we have a whole bunch of interfaces, we're gonna have to stick a whole bunch of interfaces at the top of our code, which looks pretty ugly. What's a better way for us to do this? Well, before we used import, right? We imported from simple storage.sol. For this one, what we could do is we could import from aggregator v3 interface.sol. We could go ahead and create a new contract with this aggregator v3 interface, or what we can do is we can import this directly from GitHub. If we go back to the documentation of these Chainlink data feeds, we go to using data feeds, and we scroll down, we see at the top, we have this import statement. Import at chainlink/contracts/src v08 interfaces aggregator v3 interface. This import has the same path setup as the GitHub repository for the Chainlink code. Instead of us directly adding all of the code right into our remix, what we can do instead is we can import directly from GitHub, or what's called an NPM package. Remix is smart enough to know that at chainlink/contracts is referring to the NPM package at chainlink/contracts. We'll talk about NPM a little bit in the future. It's what's known as a package manager and can keep versions of different contracts for us to directly import into our code bases. At chainlink/contracts is created directly from the Chainlink GitHub repository. So Remix downloads this code from NPM, which is created from this GitHub. So now we know that if we import at chainlink/contracts src v0.8 interfaces aggregator v3 interface.sol, this is the same as if we had just stuck this whole contract right at the top of our FundMe contract, which makes our code look a lot nicer. And now we have this aggregator v3 interface that we can work with. Okay, great. So now that we have a minimalistic interface, which will give us the ABI, how do we actually go ahead and get the price here? Well, documentation has a good example if you want to play with it and try to reverse engineer it as well. Here's how we're going to do it. In our code, we're going to create an aggregator v3 interface object called price feed, an aggregator v3 variable called price feed, which is going to equal to aggregator v3 interface contract at address, this address. Exactly the same as what we're doing down here. We're assuming a contract at this address is going to have all the functionality of this aggregator v3 interface, which again means it has this decimals function, this description function, version, get round data, and the important one, latest round data, which has the latest price at this answer piece. What we can do now is we can call that latest round data function on the price feed. So we'll say price feed dot latest round data. Now, if we look at the interface, we see that this latest round data actually doesn't return one variable, it returns a whole bunch of different variables. And that's what we're going to return in our contract. So we're going to put these parentheses and we're going to say uint 80 round ID. We can even look right at the documentation to see what else it returns. Int price, uint started at, uint timestamp, and then uint 80 answered in round. Oh, now there's a lot of code here. Since this function returns so many different variables, we have to set something up to capture them. However, all we care about is price. We don't care about round ID, started at, timestamp, or answered in round. So what we can do is just remove them and just leave the commas. And now we have int price equals price feed dot latest round data. The reason that price is an int 256 and not a uint 256 is because some prices or some data feeds could be negative here. So that it's an int 256 so it can stay flexible. Now that we have the price, this is going to be price of ETH in terms of USD. And we saw an example of this before. It was around 3,000 and it returned this number because Solidity doesn't work with decimals for a number of reasons, but we just need to know that there are 8 decimal places associated with this price feed. If you want to double check how many decimals there are, this contract has a decimals function that you can call as well that will tell you exactly how many decimals are in this price feed. Now, as we know, message.value is going to have 18 decimal places. Why does it have 18 decimal places? Well, because 1 ether is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8 is this massive number in Wei, which has 18 zeros, which is equivalent to 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So we want these to have the same decimal places, right? Because right now this has 8, this has 18. They're different units right now. So to get them to match up, all we need to do is return price times 1e10, or 1 raised to the 10th, which is equal to 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Message.value, though, is going to be a uint 256. And right now, price is an int 256. So why do we convert this value from an int 256 to a uint 256? Well, we can do what's called typecasting. All we need to do is add uint 256 and wrap this whole thing up between these two parentheses. You can't typecast anything, but there are some values like int 256 and uint 256 that can be easily converted between the two. Now, of course, since we're not modifying any state with this getPrice function, we can make this a view and say it returns a uint 256. And if we save and compile, we go ahead and we get that check mark. Now, math can be a little bit tricky the first couple of times you do it in Solidity, but the more you do it, the easier it becomes. And in the future, we can always reference a function like this to figure out, okay, here's the easiest way for me to get this number. Awesome. So now we have a getPrice function, which is going to return a uint 256, which is going to be the price of Ethereum in terms of USD. All we need to do is convert the message.value from Ethereum to terms of dollars. Let's create this get conversion rate function. For this one, we're going to take an input parameter of uint 256 of ETH amount. It's going to be a public view function, and it's going to return a uint 256. We're going to pass it some ETH amount, and on the other side, we're going to get how much that ETH is worth in terms of USD. So we're going to do a uint 256 ETH price equals get price. So first, we're going to call our get price function that we just created to get the price of Ethereum. Then we're going to do uint 256 ETH amount in USD equals ETH price times ETH amount. And then we're going to divide it by 1e18. When you're doing multiplication and division math in Solidity, you always want to multiply and add first and then go ahead and divide. Since ETH price and ETH amount both have 18 additional decimal places, if we were to just let them rock without this, they would have an additional 36 zeros tacked onto the end. So we need to divide by 1E18. Now, when we get to the hard hat sections of this course, testing all this math is going to be a lot easier. And if you're really struggling with some of the math bits right now, I wouldn't let that slow you down, because once we get to hard hat, it's going to become a lot easier to actually test this than working on a test net. And this ETH amount in terms of USD is the number that we're looking for. So we can just go ahead and return ETH amount in USD. This needs to be returns here, and boom. Now we have a get conversion rate function. To walk you through the math real quick, let's say the ETH price is going to be $3,000. So it's going to be 3,000, but it's going to have an additional 18 zeros tacked on the end. It matches the message.value way units. And let's say, for example, we send 1 ETH, or 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8 ETH into this contract. 1 ETH should equal $3,000. So to get the price, we're going to now do the ETH price, which is 3,000, times the ETH amount, which is this 1, and then divide by 1 raised to the 18. So math it out. We'll do 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8 times 3,000, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we divide that by 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which equals 2.99999E21, which the calculator kind of messed up the math a little bit, but 2.99E21 means this has 21 decimal places. So it'd be 2.12345678910 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 1, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 1, 2, 3, 4, 5, 6, 7, 8 2,999.9999999. And this is actually exactly the reason why we don't do decimal math in Solidity. Our calculator saw that massive number, was having a hard time getting it, so it ended up rounding that number to 2.999999. When we work exclusively with whole numbers in Solidity, we don't have a chance of losing that precision. And in Solidity, this is going to return exactly $3,000, which is correct. 1 Ethereum at $3,000 per Ethereum is going to be $3,000. And like I said, since we're building this contract, assuming we're going to be working on this testnet, we're not going to test this function on the testnet because we're going to have to wait for that transaction to go through. If you want to go ahead and deploy this and play around with it yourself, you're more than welcome to. Okay, great. Now we have a function called get conversion rate that we can use on our fund function to make sure we've sent enough message.value in our fund. So what we can do now is all we need to do is do get conversion rate of message.value needs to be greater than the minimum USD. Of course, right now our minimum USD is just in terms of 50, and we know that get conversion rate is going to return it with 18 zeros to represent the decimal places. Our minimum USD amount needs to be upgraded to 250 times 1E18, or again, 1 times 10 raised to the 18th. I'm going to deploy this to a testnet just to demonstrate it, but again, you don't have to if you don't want to wait for this. So I'm going to go ahead and deploy this, confirm, and now we have this fund me contract. If I don't say anything in value and hit the fund button, we're going to get this gas estimation error failed. This is kind of a blanket error, basically saying, hey, you can go ahead and send this transaction if you want. It's highly likely that it's not going to work. And the reason that Remix knows that it's probably not going to work is because it can see this require and simulate the transaction and say, hey, you didn't send enough money with this. However, even if we send some money, like 5,000 way, it'll still give us this error because that's not enough. Let's do the calculation right now based on what the price of ETH is. So we can actually go to data.chain.link. We look and see approximately what the price is. So it looks like the price of Ethereum right now is about $3,000. And this might be different for you depending on when you do that. So if the price of Ethereum is $3,000 and our minimum is at least 50, we could do 50 divided by 3,000, 0.016 ETH should be approximately enough. So if we go to our Ethereum converter and we do 0.016, we'll get how much that is in way. Let's do 0.02 just to make sure that we're going to be over the amount. So we'll paste that in. We'll change this to way. And now if I hit the fund button, instead of us getting that error popping up, it's going to actually go ahead and let us do the fund function, and we could confirm it and it wouldn't fail. I'm going to reject it for now just because I don't really feel like waiting for the transaction to go through. But great, we've confirmed that our get conversion rate is working as intended. Awesome, great work. So what's the next bit of this funding contract that we want to do? Well, when people actually send money to this contract, we want to keep track of all the people who send us money. So let's create some data structures to keep track. Let's create an array of addresses called funders, and we'll keep adding all the funders who send money to us. So we'll say an address array or an address list. We'll make it public, funders. And anytime somebody sends us money, and this actually does indeed go through, we'll add that funder to the list. So we'll say funders.push message.sender. Like message.value, message.sender is an always available global keyword. Message.value stands for how much Ethereum or how much native blockchain currency is sent. Message.sender is the address of whoever calls the fund function. So if we're on Rinkeby, message.sender is going to be equal to whatever address is calling that function. Since our address is sending the Ether, we're going to add our address to this funders list. This way we can keep track of all the wonderful donators who are donating to our contract. Then maybe we want to even make a mapping of addresses to UN256s of addresses to how much money each one of these people have actually sent. So we'll do address to UN256, public, address to amount funded. And when somebody funds our contract, we'll say address to amount funded of message.sender equals message.value. Now we have a function where people can fund our contract and we can set a value in terms of USD, and we keep track of the different funders who actually fund our contract. This is fantastic. Now, I know we've gone over a lot of really intense math and intense stuff here. So let's do a quick refresher of what we've learned so far. Whenever we work with a contract, we always need the ABI and the address. When compiled, an interface gives us that minimalistic ABI to interact with contracts outside of our project. When you combine these compiled interfaces with an address, we can call the functions on that interface on that contract. Chainlink data feeds are a decentralized way to get information about the real world. In this case, we're getting the price of Ethereum in terms of USD from a decentralized collective of Chainlink nodes. When working with math in Solidity, decimals don't work. So we need to keep that in mind when doing any type of math in Solidity. And we need to make sure we always have the correct units so that our math makes sense. Message.value and message.sender are globally available variables where message.sender represents the sender of the message or transaction, and message.value represents the number of way sent with the message. There's a whole bunch of different special variables and functions that we can access at any time, and these are available in the Solidity documentation. All right, great. We've got a great way that we can actually start funding our contract. But our code looks a little bit messy. We've got a couple of different functions for getting the price and working with these prices. Is there a way to make this math a lot easier to use? This is where we're going to introduce the concept of a library. So what is a library? I definitely recommend checking out soliditybyexample.org as you're going along with this course as well. They've got some fantastic examples. One of such example is going to be about libraries. Libraries are similar to contracts, but you can't declare any state variables and you can't send Ether. We can also use libraries to add more functionality to different values. What do I mean by that? Well, what we can do actually is we can have get conversion rate be a function of a uint256. So we could do something like message.value.get conversion rate. And we can add functions as if uint256 was an object or a struct or a contract that we actually created. So how do we do this? Well, let's create a new contract in our contracts folder. We create a new file. We're going to call it price converter.sol. And our price converter.sol is going to be a library that we're going to attach to a uint256. So how do you actually create a library? And what is a library? Well, a library is going to be really, really similar to a smart contract. It's going to start with SPDX, license identifier, MIT. We're going to give it a pragma solidity 0.8.0. And instead of typing contract for the name of the contract, we're going to do library for the name of the library. We're going to call it price converter. Now, libraries can't have any state variables, and they also can't send either. And all the functions in a library are going to be internal. So what we can do is we can go back to fundme.sol. We can grab get price, get version, and get conversion rate, copy them all, delete them from fundme.sol, and paste them into our library. And of course, since we're using aggregator v3 interface in here, we can also copy the import from fundme. And since we're not using the aggregator v3 interface in our contract anymore, and we're using it in our price converter, we can paste it into our price converter. Now, if we compile priceconverter.sol, we see that it actually passes. Now, all the functions inside of our library need to be internal. And we're going to make this library price converter different functions we can call on UINT 256. For example, we're going to be able to do message.value.getConversionRate. We're going to directly be able to get the conversion rate of a value of a UINT 256 as if that was a function for it the whole time. So first, let's make this internal. Let's make getConversionRate internal, and we'll make getVersion internal. Now that we have this library price converter back in our fundme, we can now import this price converter and attach it to UINT 256. So we'll do import./priceconverter.sol. And in fundme, we'll do using price converter for UINT 256. Of course, if we compile our fundme now, this line is getting an issue because it's saying, hey, get conversion rate isn't defined. Now in our library, the first variable that gets passed to the function is going to be the object that it's called on itself. So in fundme.sol, let's go ahead and comment out this line for now. If we do message.value.getConversionRate, this is secretly the same as if we did getConversionRate of message.value. In our price converter library, the message.value is going to be passed as the input parameter to get conversion rate. For get price and get version, we don't really care about the number, so we're just going to leave it blank for now. So instead of require get conversion rate of message.value, we can now do message.value.getConversionRate and compile that. You'll see that here we're not passing a variable, even though our getConversionRate function says, hey, I'm expecting a variable. Again, the reason for this is this message.value is considered the first parameter for any of these library functions, and that's how it works. If we wanted another variable in here, like UINT 256 something else, now we would want to pass something else in here, 123, and this 123 would get assigned to this something else. But we're going to delete that for now. Okay, great. And in doing that, we've minimized our fundme contract a lot by moving a lot of that math and price conversion stuff into our price converter library.sol. One of the most common libraries that was used for the longest time was this library called safemath.sol. And you'll probably see it a lot of different places. We're going to go off on a quick little tangent here and teach you about safemath. So let's close fundme and close price converter. And let's create a new file called safemath.tester.sol. And let's start with some basic stuff in here. Safemath was all over the place before version 0.8 of Solidity, and now it's almost in no contracts. What happened? Why is safemath no longer used as much? Well, let's create a sample contract. This is a section that you don't have to follow along if you don't want to code along with me, but if you want to, you absolutely still can. This is going to be a contract we are going to deploy on a JavaScript virtual machine. We can use any version of Solidity before version 0.8 of Solidity. So for example, we'll use pragma caret 0.6.0, and we'll create contract safemath.tester.sol. Now, if I create a UINT 8, and I set it to public big number, and I set this to 255. Oops, safemath tester. Let's go ahead and compile safemath tester with 0.6.7 pragma solidity. The maximum size of a UINT 8 is going to be 255. This is going to be the biggest number that we can fit in an UINT 8. And if I were to deploy this to a JavaScript VM or even a test network, safemath tester, let's go ahead and deploy it. If I hit big number, we're going to get 255. Well, what happens if I create a function called add that sets big number equal to big number plus 1. Let's save that, delete that old contract, and deploy. Well, right now, big number is 255. What happens when we add 1 to big number, when 255 is the max size a uint8 can be? Well, let's hit add. Now let's check what big number is. Big number gets reset to 0. So what's going on? Well, prior to version 0.8 of Solidity, unsigned integers and integers ran on this concept of being unchecked, which means that if you passed the upper limit of a number, it would just wrap around and start back from the lowest number it could be. So if I call add a whole bunch more times and hit big number, now it's 8. If I were to hit this add button a ton more times and get it back to 255, it would then continue to wrap over to 0. So one of the most popular libraries that was out there was this safe math library, which would basically check to make sure that you weren't wrapping around a uint256 or an int256. Basically, it was a way to say, hey, you've reached the max this number can be, and now your transaction is going to fail. If we switch this to 0.8 of Solidity, delete the old contract, we'll go switch this to 0.8. We'll go ahead and compile it. And now we deploy this to a JavaScript VM. If I hit big number, we get 255. But if we hit add, it actually fails and we still get 255. In version 0.8 of Solidity, they added this bit where it automatically checks to make sure if you're going to do what's called overflow or underflow on a variable. We can actually revert back to the unchecked version by using an unchecked keyword. So if we wrap this big number equals big number plus 1 in this unchecked bracket, let's delete our old contract, we'll compile, we'll redeploy. We hit big numbers, 255. Now we hit add, we hit big number again, it reverted back to 0. So that's a little bit more about safe math, checked and unchecked. So in version 0.76 and below, this code that you see in front of you is going to be the exact same as this code in 0.8 and above with this unchecked keyword. Now you might be thinking, in newer versions of Solidity, why would I use this unchecked keyword? Well, you'll find out later that this unchecked keyword makes your code a little bit more gas efficient. So if you're absolutely positive that your math is never going to reach the top or bottom limits of a number, then it might make sense for you to use the unchecked keyword. Let's head back over to our FundMe contract, where we are now using the price converter library that we just created. All right, great. So now we've got a pretty minimalistic contract here for actually doing the funding. And we have all of our math for getting conversion rates done in our library price converter, which we're going to import at the top of FundMe. Cool. So at this point, we've got our fund method. Awesome. And so we can allow anybody to go ahead and fund this contract and send this contract, Ethereum or any native blockchain currency, to this contract. Well, now what do we want to do? Well, once all the funders have gone ahead and funded, we're going to want the project to be able to withdraw the funds out of this contract so they can actually go ahead and use those funds to buy things for this project. So let's go ahead and create a withdraw function. So we'll create a function withdraw and we'll make this public. Since we're going to be withdrawing all the funds out of this contract, we probably also want to reset our funders array and our address to amount funded. Since we'll be withdrawing all the funds, those amounts should go back down to 0. So let's go ahead and loop through the funders array and update our mapping object so that each of these funders now has 0, because in just a second, we're going to withdraw all the money from them. So to do this, we're going to use something called a for loop. So what is a for loop? A for loop is a way to loop through some type of index object or loop through some range of numbers or just do a task a certain amount of times repeating. So for example, let's say we have an array or a list. And on that list, we have 1, 2, 3, 4. If we wanted to get all of the elements in this array or in this list, aka 1, 2, 3, 4, how do we get all the elements in this list? Well, we would use a for loop to loop through each one of these objects. So at the 0th index would be 1, at the first index would be 2, and at the second index would be 3, and at the last index would be 4. So we would loop through the indexes 0 through 3 to get all of these elements. Or maybe another example is if this was A, B, C, D. A is at the 0th index, B is at the first index, C is at the second, and D is at the third. And we would loop 0 through 3 to get to each one of these elements. We're going to do that exact same thing, but with the funders array. So how do we actually do that? Well, we first start with the for keyword. The for keyword says, okay, we're about to start a loop. And inside of these parentheses, we define how we want to loop through it. Also, backslash star and star backslash is sort of like brackets for comments. Anything in between these two will be a comment. So in a for loop, first we give it the starting index, then we give it the ending index, and then we give it the step amount. For example, maybe we want to start with 0, we want to go to 10, and we want to go up by 1 each time. So we'd go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or maybe we start at 0, we want to end at 10, and we go up by 2 each time. So we'd go 0, 2, 4, 6, 8, 10. Or maybe we want to go from 0 to 5, we want to go from 2 to 5, with a step of 1, we'd go 2, 3, 4, 5, etc. So this is what's going to go inside of this for bit here. So for our starting index, and let me even just put this above so that you can reference it. So our starting index is going to be uint256 variable, and we're going to call it funder index. And we're going to start with funder index being equal to 0. So we're starting with 0 here. And we're going to end with the length of our funders array, since we want to loop through all of the funders. So we're going to say funder index needs to be less than funders dot length. So our ending index is going to be whenever funders index is no longer less than funders dot length. And then finally, we're going to say funder index equals funder index plus 1, which means that every time the code inside of this loop finishes, we're going to increase funder index by 1. That's how we go from 0 to 1 to 2 to 3 to 4 to 5, etc. Another way you can type funder index equals funder index plus 1 is you can just do funder index plus plus. This plus plus syntax means funder index equals itself plus 1. So let's start looping through our funders array. To access the 0th element, or the first element, we're going to say funders of funder index. So we're saying we want to access the 0th element of our funders object. And this is going to return an address for us to use. We're going to go ahead and say address funder equals funders at the funder index. So now we have this funder address, and we want to use this to reset our mapping. So we're going to say address to amount funded at the funder key is now equal to 0. Because remember, in fund, we update the amount whenever we fund the contract. When we withdraw the money from the contract, we're going to reset it back to 0. Now, let's walk through this. Funder index starts from 0, so we're going to get the 0th funder. We're going to grab that funder at the 0th index, and we're going to reset the address to amount funded of that funder to 0. Then this for loop is going to update by 1. It's going to move from 0 to 1. It's going to check then if funder index is less than the length. Let's say funders has 10 people in it. If funders has 10 people in it, it'll still be less. So now funder index will be 1. Address funder will equal funders of 1 now instead of 0. And we'll grab that address and we'll reset that address's amount funded to 0. Then we'll continue to 2, to 3, to 4, all the way up to the length of our funders array. And this is how we can loop through our objects. So saying this middle one is the ending index isn't exactly right, since we're really checking for a Boolean to see if this is still true, but hopefully you get the idea. So we've reset the balances of the mapping. However, we still haven't done two things. We still need to reset the array to make the funders a blank array. And then we also need to actually withdraw the funds. Since when we funded this, we sent message.value along with calling this fund function. However, we didn't actually withdraw the funds. So to reset the array, we could loop through it and delete objects from this address array, or we could just totally refresh this variable. So instead of looping through the array and deleting objects, we're just going to say funders equals a new address array. We're going to completely reset the array by saying this funders variable now equals a brand new address array with 0 objects in it to start. If we were to put a 1 here, there would be 1 element to start in the array, 2 would be 2, 3 would be 3, etc. We're just going to start it as a completely blank new array. So great, we've gone ahead and reset the array, but how do we actually now withdraw funds from this contract? How do we send the funds back to whomever is calling this? Now, to actually send Ether or send native blockchain currency, there are actually 3 different ways to do this. We're going to look at all 3 and say what the differences between the 3 of them are. The 3 different ways are going to be transfer, send, and call. Let's go ahead and start with transfer, since transfer is the simplest and at surface level makes the most sense to use. So if we want to transfer the funds to whomever is calling this withdraw function, we would say message.sender.transfer, and then we'd get the balance of our contract here by saying address this. This keyword refers to this whole contract dot balance, and we can get the native blockchain currency or the Ethereum currency balance of this address like this, and we can just do that. Only thing that we need to do is we need to typecast message.sender from an address type to a payable address type. So message.sender is of type address, whereas payable message.sender is of type payable address. And in Solidity, in order to send the native blockchain token like Ethereum, you can only work with payable addresses to do that. So we just wrap it in this payable typecaster. So this is the first way that we can actually send Ethereum or send tokens from different contracts to each other. We wrap the address that we want to send it in this payable keyword. We do .transfer, and then we say exactly how much we want to transfer. But there are some issues with transfer. Here we are on Solidity by example for sending Ether, which again is a fantastic resource to refer to if you get lost. The method that we just looked at was this transfer method. Now, we saw way earlier in the course that if I sent Ethereum from one address to another, it cost about 2,100 gas or 2,100 gas. Our transfer function is capped at 2,300 gas, and if more gas is used, it throws an error. The next one that we're using is going to be send, which is also capped at 2,300 gas, and if it fails, it'll return a Boolean. So with transfer, if this line fails, it'll error and revert the transaction. With send, it won't error. It'll return a Boolean of whether or not it was successful. So using send, we'll do payable message.sender.send address this .balance. But we don't want to finish our call here. If this were to fail, the contract wouldn't revert the transaction and we just wouldn't get our money sent. So we want to do Boolean send success equals this whole bit here. And then we want to require send success. And if this send fails, we'll throw an error saying send failed. This way, if this fails, we will still revert by adding our require statement here. Transfer automatically reverts if the transfer fails. Send will only revert the transaction if we add this require statement here. So great. What's the third way that we can actually send Ethereum or native currency? Well, it's with this call command. Now, call is going to be one of the first lower level commands that we actually use in our Solidity code, because this call function is actually incredibly powerful, and we can use it to call virtually any function in all of Ethereum without even having to have the ABI. We'll learn the advanced ways to use this call much later. For now, we're just going to learn how to use it to send Ethereum or your native blockchain currency. Call is going to look very similar to send. We're going to do payable message.sender.call, and this is where we'll put any function information or any information about the function we want to call on some other contract. We actually don't want to call a function, so we're going to leave this blank. We can show that we're leaving it blank by just putting in these two quotes here. We instead want to use this like a transaction. And as we saw in our deployment, there's always this message.value bit. So we're going to use this call function as if it's a regular transaction, and we can add stuff like message.value. So in here, we're going to add these squiggly brackets, and we're going to say value address this dot balance. This call function returns actually two variables. And when a function returns two variables, we can show that by placing them into parentheses on the left-hand side. The two variables it returns are going to be a Boolean that we're going to call success, and also a bytes object called data returned. Since call allows us to actually call different functions, if that function returns some data or returns a value, we're going to save that in the data returned variable. It also returns call success, where if the function was successfully called, this will be true. If not, this will be false. And since bytes objects are arrays, data returns needs to be in memory. Now, for our code here, we're actually not calling a function, so we don't really care about data returned. So similar to what we saw with the price contract, we can just go ahead and delete that and leave the comma to tell Solidity, yeah, we know this function returns two variables, but we only care about one. And then similar to the send piece above, we're going to do require call success, call failed, meaning that we're requiring call success is true. Otherwise, we'll revert with an error that says call failed. Now, if learning the difference between these three is a little complicated for you right now, don't let that slow you down. Feel free to come back to this after you've learned more about how some of these lower level functions work and a little bit more about how gas works. Solidity by example does a fantastic job though of saying what the differences between all three are. Transfer has a maximum of 2300 gas and throws an error if it fails. Send has a maximum of 2300 gas, returns a Boolean if it fails. Call forwards all gas, so it doesn't have a capped gas, and similar to send, returns a Boolean if it is successful or if it fails. As of recording, right now, using call is the recommended way to actually send and receive Ethereum or your blockchain native token. For now, if this part's a little bit confusing for you, for now, just look at this and see, that's how we send and transfer Ethereum or native blockchain currency tokens. And I'm going to delete this part for the video, but I'll keep those comments in the code repository associated with this course. And okay, perfect. If we hit compile of fundme.sol, we do indeed see that it's passing compilation. However, there's a bit of an issue here. Right now, anybody can withdraw from this contract. So anybody can fund, which is what we want, but we don't want anyone to be able to withdraw. We only want the person who's collecting the funds to be able to actually withdraw the funds. So how do we set this up so that the withdraw function is only called by the owner of this contract? Well, to do that, we're going to set up a couple new functions. So when we deploy this contract, we want to automatically set it up so that whomever deploys this contract is going to be the owner of this contract. And then we can do some parameters to set it up so that only the owner of this contract can call the withdraw function. So how would we do that? Well, maybe we could create a function called like call me right away. And right after we deploy this contract, we call this call me right away function, which will set up us as the owner. Now that's going to take two transactions, and that would be really annoying if we had to do that. So instead, Solidity has something called a constructor. And if you're familiar with other programming language, a constructor is exactly the same as other programming languages. Constructor is going to be the function that gets called immediately whenever you deploy a contract. So if I were to deploy fundme.sol and I were to say minimum USD equals 2, minimum USD would no longer be 50 times 1e to the 18th. It would be immediately updated to 2, because constructor is a function that gets immediately called in the same transaction that we create this contract. This constructor function is going to be incredibly helpful for us because it'll allow us to set up the contract the way we want it to be. So, for example, if we want the withdraw function to only be able to be called by the owner of this contract, we can have the constructor set up who the owner of the contract is. So let's create a global variable called address public owner. And then in our constructor, we'll say the owner is going to be equal to the message.sender. The message.sender of the constructor function is going to be whomever is deploying the contract. So owner is now going to be whoever deployed this contract. And don't worry, we're going to demo all this very soon and show you everything that's going on with Etherscan and everything. Demoing this all right now might take a little bit of time because we're using a testnet. So if you want to test it all right now, absolutely go for it, but just know it'll take you a little bit longer to do so. Now that we have the owner set up, we can modify our withdraw function to make it so that only the owner can actually call this withdraw function. So at the top of the withdraw function, maybe we want to add a section. Maybe we want to say require message.sender equals the owner. A note about double equals versus equals. You can think of this single equals as a set parameter. So when I say owner is now set to message.sender. Double equals is how you check to see if these two variables are equivalent. So we're saying is message.sender the same as owner? So this is checking to see equivalence. This is setting. Checking to see equivalence, setting. So we're going to say require message.sender is equal to owner. Otherwise, we're going to throw an error saying sender is not owner. Perfect. Now we have a quick way to make sure the withdraw function is only called by the owner of this contract. Now let's say that there's a lot of functions that we have in this contract that are going to be required to be the owner. Maybe there's a lot of functions in this contract that need a whole lot of different requires. We don't want to have to copy paste this line to every single one of our functions. So what can we do? Well, this is where something called modifiers come in. So for now, we're going to go ahead and delete this line. And below, we're going to create something called a modifier. Our modifier is going to be a keyword that we can add right in the function declaration to modify the function with that functionality. We're going to create a modifier and call it only owner. And we're going to paste that line that we just made in withdraw. And underneath it, we're going to put a little underscore. What I can do now is I can take this only owner modifier and stick it in the function declaration of my withdraw function. So what's happening with this modifier? With only owner in this function declaration, we're saying, hey, for this withdraw function, before you read all this code inside of it, look down at the only owner modifier and do whatever is in there first, and then do whatever's in the underscore. This underscore represents doing the rest of the code. So now when we go call the withdraw function, we actually do this require statement first and then call the rest of the code. If this require statement were below the underscore, this would tell our function to go ahead and do all this code first and then run the require. Because again, we have this only keyword. We're saying, great, we've got a function, it's withdraw, it's public. Oh, only owner modifier. Let's look at how that works. Okay, it tells us how to do all the code of the original function first. So let's go ahead and do that. Okay, now we're done. Now what do we do? Okay, now we'll run the require. We want to go ahead and put the require here first. So this is how modifiers work and how we can use them to improve our functionality. All right, awesome. We have all the basic functionality of our contract that we need here. Now we're finally actually going to run everything on a testnet and see everything happen live before our eyes. Are you ready? Let's do this. So let's go over to the deploy tab and we're going to switch, of course, to injected web 3. Remember, we're using injected web 3 because our price converter.sol is using Chainlink oracles that actually exist and are actually monitoring the RinkB network for us. Now we're going to scroll down to, and we're going to choose the FundMe contract, and we're going to go ahead and deploy. Once again, we want to make sure we're on the RinkB testnet, and we have a little bit of RinkB ETH in our wallet. Let's go ahead and deploy, confirm, and we'll wait a little bit, and I'll pull up our log here, and we'll wait a little bit for our contract to get deployed. All right, great. It looks like our contract has indeed been deployed. If we scroll down, we can see all of our functionality. Minimum USD is going to be that $50, but with 18 zeros so that the units are the same as Ethereum. The owner of our contract was set to our address. The instant we deployed this contract, it was deployed by calling our constructor function. So this address 0x1066 is going to be the same as the address in our MetaMask. Your address here, of course, is going to be a little bit different than mine. We have our funders array, which of course is going to be blank. We have our address array, which is also going to be blank. And then we have two functions that we can use to modify the state of the blockchain. Withdraw is going to be orange because we're not paying any Ethereum. We're actually gaining Ethereum or whatever native blockchain currency. Fund is going to be red because fund is a payable function that we are going to be sending Ethereum to, or sending whatever native blockchain currency that you're working with. So let's go ahead and see how this all works. So first, let's go ahead and fund this contract. Again, funding, we got to do a little bit of math. Right now, since the price of ETH is around $3,000, and we're looking for $50 minimum, we can do 50 divided by 3,000. We can do 3,000 divided by 50. We can do 50 divided by 3,000. So we know that around 0.02 Ethereum should be enough for this contract to work. So 0.02 Ethereum is this much way. We can copy that, paste that into here. So when we hit fund, it should actually pass. And we do indeed see MetaMask pop up, and we'll go ahead and confirm. Once this transaction goes through, we'll be able to see this contract on Etherscan with the funds in it. Now, if we don't add way here, if we don't add a value, once again, we hit fund, we'll say gas estimation failed because we're not sending enough here. And in fact, we even see execution reverted, didn't send enough. We can absolutely send this transaction, however, it's going to fail. Great, so now that our transaction has gone through, if we go onto the RinkB Etherscan, once we wait a little bit for it to finish indexing, here on the RinkB Etherscan, we can see that transaction actually went through for doing the funding. We can actually see a lot of different details going on with this transaction as well. And if we scroll down, we can see all the information about us calling this fund function. Gas limit, gas usage, the gas fees, gas price, and we can see the input data as well. We can see that we called the fund function down here. We'll learn more about the input data later. If we go to the contract that we deployed, we can now see two transactions. We can see our contract created transaction, and we can also see we called a fund method. And if we look at the balance of our contract, it now has 0.02 Ether, which makes sense since we just sent it 0.02. If we put that at 0.02 ETH in terms of way back into the value section and we call fund again, after this transaction goes through, we should see this number go from 0.02 to 0.04. Now, after we wait a brief delay, we do indeed see the balance has gone up to 0.04, which is exactly what we'd expect. Awesome. So our funding mechanism is working correctly. And if we go down into our array and our mapping, we do address to array and we paste our address, we should see the 4 number show up. And if we go to funders of 0, we see our address. And if we go to funders of 1, we also see our address. And we see that, and we see this call going through. If we go to funders of 2 in our log over here, we actually see that we get an error. An optimization that we could make to our contract in the future is to check to see if an address is already in the funders array and then not add it if it's already there. Now, let's go ahead and try to call this withdraw function, but let's try to call it with a different address than the address we originally deployed this contract with. So to do that, scroll all the way to the top of this here, and I'm going to go to my MetaMask, and I'm going to switch to a second account and hit connect. Now, our remix should be updated with the new account that's in here. You'll see that if I switch back to account 1, it switches back to account 1 so long as they're both connected. You can see which accounts are connected to applications by clicking this connected button and see which ones are connected. If you ever want to disconnect an account, you can click the 3 little dots and hit disconnect the account. And now we can see that this account is not connected. However, account 2 is connected. Let's go back to account 1 and connect account 1 so that both of them are now connected. But we'll switch to account 2. Let's switch to account 2 because again, account 2 isn't the owner of this contract. We scroll down to owner. We can see owner is 0x1066 something something, and account 2 is 0x043 something something. Awesome. So what do you think will happen when we hit withdraw here? Well, our modifier only owner should kick in, and we should get notified that if we send the transaction, we'll get this error, sender is not owner. So let's try it. Gas estimation failed. We do get this error, sender is not owner, which is perfect. This is exactly what we want. We could absolutely send this transaction if we wanted to, but that would just be a waste of gas because this transaction is going to fail. However, if we switch back to account 1 and we hit withdraw, MetaMask will pop up, enabling us to hit confirm and withdraw the Ether out of this contract address. Now, if we look at this contract address on Etherscan, after a brief delay, we'll see the balance go from 0.04 back down to 0, and we'll see our wallet balance go up from what it is back to 0.04 plus what it was. And after a brief delay, you can see our balance is indeed back down to 0. In our contract now, if we do address to amount for our wallet address that was doing the funding, it's back down to 0. And if we try to check the address of funders at index 0, we get call to funders.fundme errored, execution reverted. We've completed all the basics of this section that I wanted to go through. And you should be incredibly proud of yourself for getting this far. You've just deployed a really advanced smart contract. We're using a library and chain link contracts to build some of the most powerful applications on the planet. We've learned to use a library for any type we want in our smart contracts. We've learned more about multiplication and then units of measure in Solidity and smart contracts. We've learned about mappings, more about arrays, what the constructor does. We've learned how to send money. We've learned about for loops. We've learned about the different ways we can actually send money, at least from a low level. And we've learned about modifiers. This section is one of the tougher sections in this course. So if you completed this, you should be incredibly excited. We're going to go through our code now, and we're going to make a number of tweaks. Now, this section, we are going to do a little bit more advanced Solidity here. So if you get a little bit lost, don't sweat it too much. And feel free to try some of this stuff in the future on your own. We're going to modify this contract to make it a little bit more professional. It's not going to be end-to-end amazing, but it's going to be a little bit better, and you'll see why in a minute. So the first thing that we're going to do is we're going to look at some of these variables here. In particular, owner and minimum USD. Owner gets set one time in our contract here, and then it never changes again. Minimum USD gets set one time, even outside of the constructor. If we have variables that only get set one time, we can actually use some tools in Solidity to make them more gas efficient. For now, let's compile our FundMe contract and then deploy it to a JavaScript virtual machine. Remember, we can go ahead and deploy it right now. However, funding and withdrawing and doing any of the money stuff isn't going to work because again, we don't have a chain link network on our JavaScript VM. So those aren't going to work so well. But for what we're going to do right now, we don't really care so much. Here's what we do care about. We do care about how much gas this costs to actually send. We do care about how much gas this costs to create. Right now, creating this contract costs about 859,000 gas. And we're going to add a couple of tricks right now to bring this number down. We're going to add some stuff back in a bit, which will bring it back up. But for now, we're going to learn some tricks to bring this number down. The two tricks that we're going to learn are the constant keyword and the immutable keyword. In their Solidity, there are two keywords that make it so that your variables can't be changed. And those keywords are constant and immutable. You can learn more about them in the Solidity documentation. If you assign a variable once outside of a function and then never change it, so if it's assigned at compile time, you can go ahead and add this constant keyword. We'll learn later about storage, but when you add a constant keyword, this minimum USD no longer takes up a storage spot and is much easier to read to. So now if we recompile this and we deploy this new contract, let's see if we saved any gas. If we look in the transaction logs now, we can grab the transaction cost of how much this cost to deploy. And let's compare it to how much it was before. Wow, we saved almost 19,000 gas. That's almost as much gas as it cost to send Ethereum. Typically, constant variables have a different naming convention. Typically, you'll want to do them all caps, like min, emum, underscore, USD. So all caps with underscores. So now let's just find minimum USD and replace that with all caps as well. With this interaction, we know that this variable is a constant variable and it's much cheaper to read from. Now, if we go ahead, compile this and redeploy in our FundMe contract, even though this is a view function, remember, view functions do have gas costs when called by a contract. As a constant variable, we can see the execution cost of this variable, 21,415 gas. So let's put a little note right underneath it. If we remove the constant variable, we delete this contract, we redeploy, we click FundMe, and we hit minimum USD again, we can now see how much gas this was cost if it wasn't a constant variable. We can see the gas cost did indeed go up. Now on chains that are much cheaper, this gas difference probably won't make it that much of a difference. But on more expensive chains like Ethereum, this is going to make a big difference. For example, on Ethereum, we can actually see current gas prices on Ethereum here. We can see that the current gas price of Ethereum is about 141 Gwei. So we'll go to our converter, Gwei to Wei, we'll copy the Wei price, times this, we'll get the gas price of calling our minimum USD, which is this number here, which if we put back in our Ethereum unit converter, we can see costs this much gas. And if we times that by the approximate current price of Ethereum, which is around $3,000, calling minimum USD as a constant is going to cost $9. Calling this at a non-constant is going to cost almost an entire dollar more. You can see how all these little gas optimization tricks are going to make your life a lot better. So let's keep this constant keyword in here. We'll learn more about constant and storage in later sections of this course. Now, as you're just getting started with this course and with Solidity, do not struggle and do not worry about making your contracts as gas efficient as possible. In the beginning, and especially right now, just write your contracts as best as you can. Once you get really good at gas and once you get much later on in the course and much more advanced with Solidity, then you can start going back and working on gas optimizations. But do not let gas optimizations hold you back, or if you start stressing over it, just let it go. Don't worry about it and just write your code as best you can. So long story short, do not stress about gas optimizations right now. Now, another variable we only set one time is going to be our owner variable. Owner equals message.sender. We set this one time in the constructor. Variables that we set one time, but outside of the same line that they're declared, and we set them, for example, in the constructor, we can mark as immutable. Typically, a good convention for marking immutable variables is going to be doing I underscore, so that we know that these are immutable variables. They have very similar gas savings to the constant keyword. Owner, of course, is a variable that we can't set on the line here because inside the global scope, there's no function going on. However, inside functions, because inside the global scope, there's going to be no message.sender. There's only going to be a message.sender when we're inside of a function. So inside here, we might say iOwner equals message.sender. And then of course, we'll scroll down and we'll change this require only owner now equals iOwner. Now, if we compile that and deploy it, we can see how much gas calling iOwner is going to be with the immutableness. We get 21,508, which we'll go ahead and copy for now. And we'll put right here. We'll say immutable. Now, if we remove the immutable keyword, let's close this, redeploy. Now, if we scroll down to iOwner, scroll up the logs, we go down to the call, we scroll down, we see the execution cost was much more. So we'll do double backslash, paste that in here, gas for non-immutable. So you'll want to keep some of these tricks in mind when it comes to storing variables. The reason that these two save gas is because instead of storing these variables inside of a storage slot, we actually store them directly into the bytecode of the contract. And like I said, don't worry too much about that for now. Later on in the course, we'll teach you more about storage and a lot of this low-level stuff that comes with these contracts. But for now, just know that these exist and they're nice gas savers if you're only setting your variables once. All right, great. So we've just made our contract a little bit more gas efficient. Little gas efficiency improvements are going to be concepts I sprinkle throughout this course. And when we get to the more advanced section, I'm going to break down exactly what's going on and why all these gas efficiencies exist and what's going on behind the scenes for these gas efficiencies to occur. It's a little bit in the weeds, which is why I'm going to gloss over it right now. So if it's confusing, don't worry. I wouldn't let these gas efficiencies be the thing that slow you down. Awesome. So we have these two gas optimizations. How else can we make this contract a little bit more gas efficient? Well, one of the ways we can make this more gas efficient is by updating our requires. Right now, with our require statement, we actually have to store this sender is not an owner as a string array. Every single one of these characters in this error log needs to get stored individually. This string may not seem very big, but it's a lot bigger than the alternative with what we can do. As of 0.8.4 of Solidity, you can now actually do custom errors for our reverts. We declare them at the top and then use ifs instead of require, and then just add our revert statements. This ends up saving a lot of gas since we just call the error code as opposed to calling the entire string associated with the error. So for example, with our require down here, and with all of our requires, what we could do is instead of having this require, we could create a custom error. So at the top, what we could do is we could say error, not owner. And you'll notice that this is actually outside of the contract here. Now what we can do is we can take this error not owner, scroll down into our only owner. Instead of doing a require, we'll do an if statement. We'll say if message.sender is not iOwner, then we're going to go ahead and revert with a not owner error. This ends up saving us a lot of gas since we don't have to store and emit this long string here. Now, in a lot of code today, you'll still see require a lot of places because these custom errors are pretty new in Solidity. So you'll want to get used to writing it both ways. I wouldn't be surprised if in the future, the syntax for some of these errors looks like this so that it's more readable. But for now, if you want to do a more gas efficient way than requires, you can use something like this. We could update all of our requires here for these custom errors, but for now, I'm going to leave both in just to show you the differences. This revert keyword does the exact same thing that require does without the conditional beforehand. So you can actually go ahead and revert any transaction or any function call in the middle of the function call. Now let's look at one more way to improve this contract. Sometimes people will try to interact with a contract that takes Ethereum or the native blockchain token without actually going through the required function calls that are needed. For example, on a JavaScript EVM here, I could actually try to send this contract money without calling the fund function. However, if I were to do that, what would happen? Would our fund function get triggered? No, it wouldn't get triggered. We wouldn't keep track of that funder. We wouldn't have that person's information updated in this contract. So if later on we went to give rewards or something, we wouldn't know about those funders. And this wouldn't be great because people would send our contract money without us ever knowing, and we wouldn't be able to give them any credit or anything. Additionally, Maybe they called the wrong function by accident and they weren't using MetaMask and they weren't using a tool to tell them, hey, this transaction is likely going to fail. So what can we do in this case? What happens if someone sends this contract ETH without calling the fund function? Right now, if we were to send this fund me contract ETH, it would just go to the contract, right? And this contract just wouldn't keep track of those people. But there's actually a way for when people send money to this contract or people call a function that doesn't exist for us to still trigger some code. And now there are two special functions in Solidity. One is called receive and one is called the fallback. Now, in Solidity, there are actually a number of special functions, and two of these special functions are the receive special function and the fallback special function. A contract can have at most one receive function declared using the receive external payable without the function keyword. This function cannot have arguments, cannot return anything, and must have external visibility and a payable state mutability. What does that actually mean and or look like? Well, let's create a separate contract to go ahead and play with this. So in here, we're going to create a new file called fallback example.sol. And in here, we're going to add our basic pieces: SPX license identifier, MIT, pragma solidity, 0.8.7, and we'll do contract fallback example, like so. Feel free to pause the video to catch up to this point. Once we create our fallback contract, let's create a variable to go ahead and try to test this function. We'll create a uint256 public result variable. And let's create this receive function. So we'll say receive is going to be an external payable function. We don't add the function keyword for receive since Solidity knows that receive is a special function. Whenever we send Ethereum or make a transaction to this contract now, as long as there's no data associated with the transaction, this receive function will get triggered. What we can do in here now is we can say result equals 1. So let's go ahead and test this out on the JavaScript virtual machine. So we compile this. So we're going to go ahead and compile this. We'll go deploy it on the JavaScript virtual machine. We're going to deploy our fallback example, and we're going to see what result is initialized to. Since we haven't set anything for result, of course, is initialized to 0. But what if we were to send this contract some Ethereum? Well, receive would go ahead and be triggered here. We can actually send this contract some Ethereum directly by working with this low-level interactions bit here. Don't worry about what call data means for now. Just know that this area down here is a way we can send and work with different functions. And we can add parameters to this transaction by going up here and adjusting the variables up here. If we keep call data blank, it'll be the same as if we were in MetaMask and just hitting send and then choosing this contract address. Again, we can't actually use MetaMask since this is a virtual machine and not one of the networks that we're working with. So if I do, for example, I change this value to one way and I keep everything blank and I go ahead and hit this transaction button, which again, is going to be the same as hitting this send button, but only sending one way, what do you think will happen? Well, let's try it. We can see in the log area that we did indeed send a transaction. And if you look at the description here, you can even see it says from so-and-so to fallback example dot receive. It looks like it called our receive function, which should have updated our result to 1. So if we hit result now, we can indeed see that result has been updated to the value of 1. Well, let's go ahead and delete this. Let's deploy this contract again. And this time, let's have value be 0. Does receive get triggered this time? So let's pull this down. Let's hit transact. Let's leave the call data blank. We'll leave value at 0. So this will be the same as if we had sent 0 Ethereum to this contract. Let's hit transact. It looks like that went through. Do you think result is going to be 1 or 0? If you thought 1, you were correct. Our receive function gets triggered anytime we send a transaction to this contract now, and we don't specify a function and we keep the call data blank. When working with any other contract, like FundMe, for example, when we call one of these functions, we're actually just populating this call data bit with certain data that points to one of these functions up here. If we send a transaction and we add data to it, we could actually call one of these functions. Now let's try this again. Let's delete the contract again. We'll redeploy, open this up. Result is currently 0. Receive, like I said, only is triggered if our call data to it is blank. Now this time, if I add some call data to this transaction, do you think receive will be triggered this time? If we hit transact and remix, we actually get a pop-up saying fallback function is not defined. This is because whenever data is sent with a transaction, Solidity says, oh, well, since you're sending data, you're not looking for receive, you're looking for some function. So let me look for that function for you. I don't see any function that matches the 0x00. So I'm going to look for your fallback function. Remix is smart enough to know that we don't have a fallback function. The second special function in Solidity is called the fallback function. This is very similar to the receive function, except for the fact that it can work even when data is sent along with transaction. So our fallback will look something like this. Fallback, external, payable, result equals 2. Fallback is another one of these functions where we're not going to put the function selector because Solidity is expecting this. Actually, you're already familiar with one other special function. If we go back to our FundMe, our constructor, for example, is another type of special function. There's no function keyword. Solidity knows that this constructor is immediately called when we deploy this contract. So now we have our fallback function. Let's go ahead and compile this. Let's delete our old contract. Let's go ahead and deploy this new contract. Let's click here. We hit result. We do indeed see it's set to 0. Now, if I add this 0x00 and I send this and I hit transact, this is equivalent to calling our contract here without a valid function. So our contract goes, I don't recognize what you're trying to tell me here. I'm going to refer you to our fallback. And now if we hit result, we see that it's been updated to 2. If we take this away, Solidity will go, it looks like you're trying to send some Ethereum or call this contract without specifying what you want to do. Well, I have a receive function, so I'm just going to go ahead and forward you to that. So if we call transact, we hit result, we see it updates back to 1. Add some data, hit transact, we see it updates to 2. No data, updates to 1. SolidityByExample.org has a wonderful little chart that we can use to figure out whether or not receive is going to get triggered or fallback is going to get triggered. If it is empty and there's a receive function, it'll call the receive function. If it is data and there's no receive function, it'll just go to the fallback function. And if there's no fallback function, it might error out. So this is a lot of really fantastic information here. How can we apply this to our FundMe contract here? Well, what we can do now in our FundMe is we can add these fallback and receive functions just in case somebody actually sends us contract money instead of calling the fund function correctly. So what we can do is let's add a receive function. So if somebody accidentally sends it money, we can still process the transaction. We'll say receive is going to be external payable, and we'll just have the receive function call fund. And we'll do the same thing with our fallback function. We'll have fallback external payable. We'll just have it automatically call fund. Now, if somebody accidentally sends us money without calling our fund function, it'll still automatically route them over to the fund function. This means too that if somebody doesn't send us enough funding, that transaction will still get reverted. So let's go ahead now and let's switch to Rinkeby to test this on a real testnet. I'm on Rinkeby in my MetaMask. Let's switch over to Injected Web3. And we'll scroll down, we'll choose our FundMe contract, and we'll go ahead and deploy this. MetaMask pops up. I'm going to go ahead and confirm the transaction, and we see our FundMe contract here. Right now, we can see I'm the owner, we can see minimum USD, and we can see, of course, that it's a blank contract and there's nothing funded in here. If we copy the address and then go to Rinkeby Etherscan, paste the address in, we can see that there's no Ether in here, and the only transaction associated with this has been the contract creation. We saw what happened before when we hit the fund function. Our contract was updated with a new balance, and that funder was added to our array. Let's see what happens now if we just directly send this contract money without calling the fund function here. If we did this right, our receive function should pick it up and kick the transaction over to fund. So let's copy this address We'll go to our MetaMask. We'll hit send, paste the address in here. We'll do 0.02 ETH again, because this should be more than the minimum amount in USD. We'll hit next. I'll go ahead and confirm this. And after a slight delay, if we did this right, we should see this transaction having called the fund function here. Now that our transaction has gone through, and after a brief delay and waiting for Etherscan to update, we do indeed see that our balance has updated to 0.02, which of course, this makes sense. And we see in the transactions list here, we see that this actually went through as a transfer instead of us calling the fund function. Let's go ahead and remix and see if our funders was updated. It looks like it was. At the 0th position of funders, we have our address. And if we take our address and pop it into address to amount funded, we can see exactly how much we had funded. This means that since we added this receive function in here, we automatically had to call our fund function up here. So awesome work. We were able to add a receive function to help people who accidentally call the wrong function or accidentally send this contract money instead of correctly calling the fund function. Now, if they had directly called the fund function, it would have cost them a little bit less gas, but at least this time they're going to get credit and added to our funders array for having sent our funding contract money. We've even learned some advanced sections of Solidity. And this is going to be the last time that we start our projects in Remix. We're going to be moving over to a code editor now where we can get even more advanced with our Solidity and our setups. For the most part, you've gone over the vast majority of Solidity basics. There are a number of things that we still haven't learned yet. And the reason we haven't gone into them is because they get more advanced and understanding their real use doesn't really make too much sense until a little bit later. Some of the things that we're going to go over are enums, events, try-catch, function selectors, ABI encoding, hashing, and then YUL/assembly. However, if you've gotten this far, you probably can read most Solidity code and understand what's going on, which is absolutely fantastic. So you should give yourself a huge round of applause for getting this far and doing this. Let's do a quick summary of this more advanced section and make sure we understand what we learned. In Solidity, there are a couple special functions. Some of them are receive, fallback, and constructor. These functions don't need to have the function keyword and instead can just be called like so. Receive and fallback are two very special functions. If data is sent with a transaction and no function was specified, the transaction will default to the fallback function if that fallback function exists. If data is empty and there's a receive function, it'll call the receive function. There are a couple of keywords that can help us save gas in the long run. Some of those keywords are going to be constant and immutable. Constant and immutable are for variables that can only be declared and updated once. Once we say minimum USD is 50 times 1E18, this minimum USD can never be changed again. And this helps us save gas. Immutable can also save gas similar to constant. However, immutable variables can be declared one time in the constructor. Once an immutable variable is declared, it can't be changed later on. In fact, if we even tried to update an immutable variable or a constant variable, and we compiled, our compiler would give us an error saying, can't write to immutable here. Or if we tried to change a constant variable, our compiler would say, hey, you can't assign to a constant variable. Sorry. In Remix, if we want to send Ether to a contract that's on the JavaScript virtual machine, we can deploy that contract. And then in the contract, we can just hit the transact button without any call data and update the value that we send with the transaction. If call data is blank, it'll trigger a receive function if it exists. But if there's data that doesn't specify any of the other functions, it'll trigger the fallback function. Awesome. You've done fantastically to get this far. And for this section, before we get started actually moving